Hi, I'm Dr. Fred DePiero, and this is an introduction to circuits. In this video, we'll talk about applying Ohm's law, V equals IR, with correct units. We'll describe why current flows in a circuit and describe the differences between DC and AC circuits. We do assume an introductory exposure to voltage, current, and resistance and to common circuit elements such as you would have in a prerequisite physics course. With the goal of demystifying current flow, hey, did you ever touch a 9-volt battery to your tongue? That will take some of the mystery away. Respectfully, don't do that with a 12-volt car battery. It's quite dangerous. 12 volts is enough voltage to penetrate the body. There's plenty of current to stop the heart in a car battery, and there are chemical hazards. It's not a joke. Now, two conditions are necessary for current to flow. One, we need an electrical energy source, and two, a closed path of conducting material to support the flow of electrons. In a battery, the energy source is a chemical reaction. That reaction causes a separation of charge, and one battery connection ends up having excess electrons, and the other battery connection, or battery plate, as it's called, has a deficit of electrons. The closed path can be accomplished by having wire and components, such as resistors, that provide a continuous route from the region with an excess of electrons to the region with a deficit. We can make an analogy to this. The energy source is like a water pump, and the closed path is like a piping network. Ever build a battery from a lemon, galvanized nail, and a penny? It works. I'm not making this up. The chemical reaction results in a concentration of electrons on a zinc nail, we'd call the minus terminal, and a deficit of electrons on the copper penny, which we'd call the plus terminal. Note that electrons are not created or destroyed in this process. They're just moved around between the plates of the battery. If we introduce a conducting path between the terminals, the battery terminals, that permits electrons to flow from the overcrowded region to the deficit region. Here's a schematic of a circuit. A schematic is a logical abstraction. This includes a battery and a resistor with wire connecting them. Now, the schematic is a logical abstraction. It doesn't show the physical routing of wire and components, but the logical connectivity is the same between the schematic and the physical layout. The minus terminal, shown here, the shorter line, has an excess of electrons. The plus terminal, up here, has a deficit. And when the conducting path is established, in this case through the resistor, electrons move because like charges repel. So those excess electrons that are on the minus terminal here, they're overcrowded and they're all repelling each other. They flow through the wire. Electrons in the conduction band of atoms in a metal are free to move between atoms. If the conducting path is broken, we call that an open circuit, then the current stops. And when a battery's chemical process is depleted, it can no longer separate charge on the two plates, the two terminals, so the current stops. Please recycle. In case you're wondering, hey, why do rechargeable batteries die? Well, just as a side note, the charge and discharge processes result in a gradual accumulation of filmy deposits on the internal battery plates. This process is called sulfation. That chemical film reduces the surface area for the chemical reaction, so eventually it just can't be recharged anymore. Now, just so you know, EEs use what we call conventional current flow from plus to minus. This is exactly the opposite of the true electron flow. No disrespect to electrons, electricians. Electricians follow the electron flow. DC and AC. What do these terms mean? Well, AC refers to alternating current. In this case, the current direction changes, and it does that because the source has a positive and negative polarity that keeps changing or alternating. The AC source for power in the U.S. is in the form of a sine wave. It's not a discrete change plus to minus, it's a gradual change. DC stands for direct current, and there the polarity of the DC source is constant, and thus the current direction doesn't change. That's the case with a battery. One terminal of a battery is plus. It's plus today, it's plus tomorrow, it's plus the next day. Doesn't change. Same thing with the minus. Okay? So if you introduce that battery into a circuit, the current direction is going to flow in just one direction. We call that DC. Now, how much current flows? Well, Ohm's law, of course, tells us that. V equals IR, V in volts, I in amps for current, R resistance in ohms. This symbol here emphasizes the idea that the voltage is across an element, R, and the current is through that element. Current describes the number of electrons flowing in amps. An amp is a coulomb per second. A coulomb is a heck of a lot of electrons, 6 times 10 to the 18th. Again, current's flowing through that element. Voltage describes the amount of energy per charge in volts. A volt is a joule per coulomb, and the voltage is present across an element. Occasionally we work with conductance instead of resistance. Symbol is G. It's 1 over R. Units are referred to as either Siemens or Mohs. It's convenient when describing conductivity of low resistance materials such as wire. Okay, let's talk about how fast current actually flows in a circuit. And we need to distinguish between two things: the speed of electron flow and the speed of signal propagation. Speed of electron flow is a little bit easier to understand. It's just how quickly do the actual electrons move, the individual electrons moving through the conductor from atom to atom. Speed of signal propagation is a little more unusual. Imagine if an electron enters one end of the wire, its charge repels nearby electrons. Those nearby electrons repel their neighbors further down the wire. So this notion of signal propagation is the idea of the speed at which the effect of these repelling charges propagates down a conductor. Now the electron flow for standard conditions, DC, 10 amps, 12 gauge copper wire, that's like wire you'd have in your home for outlets, room temperature, that kind of thing. Electrons move at about 1/5 of a millimeter per second. That's pretty darn lazy. That's not very fast at all. Signal propagation is about 95% of the speed of the light. Yeah. As another side note, let's talk about how electrical units relate to other physical units. We'll start with power in watts. So watts is joules per second or Newton meters per second. Now, an electrical source influences specific kinds of particles within the volume of a conductor. Those are electrons, of course. We introduce the electron density, P, together with the volume, meters cubed, into this above equation. So we have Newton meters per electron, and then we have electrons per second. This has the form of joules divided by number of particles per second. And of course, as I mentioned, our favorite particle, the electron, and we have a favorite number of them too, 6 times 10 to the 18th. Put that in, we have joules per coulomb, coulombs per second, and that's exactly the definition of volts times amps. So we related mechanical power in watts to electrical power, volts times amps. Now, in this equation, the term on the left here was eventually associated with voltage. We simplify the meters and we actually get units of pressure here. This justifies a useful analogy between voltage and pressure and current and flow. We can make an analogy between voltage, for example, being the water pressure of a pump, and current being the amount of water flow through a pipe that results from that pressure. Resistance is simply the restriction to flow. Now that water analogy works, but there's a caveat. Notice that electrons don't fall out of the end of a wire when we disconnect the wire, at least not an appreciable number compared to the total number that are inside the wire. Now you take a pipe out of a plumbing system, drop it on the floor, and water's going to spill all over the place. This is a difference in the way the two types of systems behave. So we have a stipulation. For the analogy to work, we have to use what I'll call our magic pipes. Magic pipes come full of water that never spills out. They never have any air gaps between sections of the pipe that are joined together. So imagine you go to the hardware store, you get a supply line for the sink. When you buy that supply line, it's full of water already. You go and install it under the sink, and there are no air gaps that are introduced. If we introduce this caveat of magic pipes, then the water flow analogy will work. Water flows from the plus high pressure side of the pump and is drawn into the low pressure side. When the power source is activated, the electrons, or the water flow, begin instantaneously. So, in this video, we've talked about Ohm's law, V equals IR. We've talked about the units. We've described why current flows in a circuit and described the differences between DC and AC circuits. And hopefully the water analogy will be helpful to you when thinking about current flow.